Thanks for the introduction, and it's happy to be back at Amrita and giving a talk on something that I worked in the past at the university itself, and also happy to see a lot of people who were my professors back when I was in undergrad attending this, and also as I'm talking on this topic, must mention is Professor Ritvik, who I wrote a paper on the same topic when I was in my undergrad year back in 2014. And if you guys are interested further, you can read my paper with the Professor Ritvik here on the topic, and it's called A Simple but Complicated Survey on Quantum Computing. Yeah. I guess, it's it's a light paper to read, especially today after 10 years. It might not be the paper that you would want to read, but it's a good read. Do give it a shot when you guys have some time. And coming back to today's topic, uh, let me share my screen first. Just give me a second. Okay, so getting into presentation. Okay, yeah. One second. I'm just setting up my Windows so that I can be handy with all that. I hope my screen is visible to all of you. And okay, so like Siddharth just mentioned, I've been working as a as a software engineer at Intel, and one of the biggest problems that Intel Foundry facing is, as we go down the size of each node that we are having issues because the closer we get in the classical world for the development of CPU and in making a chip, the smaller the size, more closer you get to the atomic level of a particle. And 2 nanometer, and Intel is developing something sub 2 nanometer as well, which is 1.8 Armstrong and 14 Armstrong as well. The problem that a lot of the design engineers on the fab side face is that it gets a lot of interactions that subatomic level as well, which is not the intended thing for chip design in the classical framework. And it's also a reason why chips are not uh, at times being of best yield quality and at the initial stage of node development. And one reason why the Moore's law, as you know, which is something that has defined computational power over the years, is becoming harder to keep up with. And that's where I would say quantum computing comes in play. And quantum computing uh, is something that is a thought which just began in, I would say, late 70s, and it was part of, and in early 80s when Dr. Feynman said that if you got to solve issues that are got to do with much important problems in the nature, you need to get into quantum level because classical is too linear. And coming to that is where there was this idea of a quantum computer coming up, and then uh, people tried a lot of possibilities, and viable options started coming up early in 2000s. And I guess uh, over the years it has improved, and there are now various types of quantum computers as well, and not just earlier it used to be something that have stuck to labs, and you can only see these quantum computers through the highly cryogenic systems that they are working on. But now there are options coming up where they're trying to make it much stable in room temperature as well. But the yield, the quality is still a issue there. But coming to the next slide. Okay, so as I was saying, it's something that's gonna redefine what Moore's law is, and obviously the speed is what is gonna be the best thing that's gonna come out of quantum computing. By here, speed is something exponential compared to what a classical computer does, and it's totally uh, out of use when it comes to a normal classical computing computer and its user, it's going to be totally out of the world. And also, this does bring a requirement to have multiple development in the side of algorithms and protocols, because classical algorithms are not going to work here. And I'll be talking about why in later slides. And I just want to introduce these topics. One is it's gonna break the fundamentals of Moore's law. The second thing is it's gonna give us more computational speed, and the third one is it's gonna redefine us, and also it would require us to do more on redefining the present algorithms and other protocols that we have. Uh, Coming to this slide, okay, so as all of us know, the Shannon bit, that is the zeros and ones that's there in the classical computing world, is easily you can imitate a zero or a one without disturbing its state. Like, let's say a switch itself is a example of a binary system where the on and the off is one setting each, and it's based on electrical impulses in classical computing, and each electrical impulses can either it's an on state or an off state for a transistor that's at the lowest level in a processor. And this can easily be replicated because it's either powered up or powered down, and that's one of the features of a Shannon bit. And it's indifferent to being measured. By indifferent, I mean that uh, let's say you take a transistor and you can check measure the value of it or not, like whether it's in a zero state or a one, and it's independent from other transistors. But I am adding the caveat here that when you go really down in size, there are loss and loss of quality. So as I was talking about earlier, why companies are finding, like, in the real world, to develop processes that give you good chips at a very small nanometer level, and 2 nanometers seem to be the level where issues are starting to pop up. And further down the line as we go, it's going to get harder and harder to make chips in the classical world, with so much of chip density where already billions of transistors are packed together. Uh, okay, uh, so let's say a Shannon bit is like a decisive person. It knows whether it's a zero or a one. And when you look at a Shannon bit, which is the binary bits that we are used to, it can, like I said, it can be copied, and you can make, let's say, we can have the same thing replicated around uh, uh, whatever process that we're trying to do. And in the non-classical world, when it comes to quantum computing, it's the main thing that is uh, standing out from a normal conventional bit is uh, the basic unit, which is called a qubit, can be in a superimposed state. It can either be a zero or a one. And the main reason why that happens in case of a quantum computer is that uh, over here, it's not the electrical impulse or the signal that is triggering that measurement that we are looking for. It is actually the basic unit is fundamental part of a photon, and the photon has different spins. Like it can have a linear or a circular spin. Depends. You can just classify photons into the various spins, and that spin, which is a fundamental part of the photon, can define a qubit. The, let's say it spins clockwise and anti-clockwise, or it spins with a upward orientation or downward orientation. It can all be two. It can be used to define two different signals, and because it's a photon, it can also be in a partial state of both. Let's say I'm taking the option of having an upward spin photon and a downward spin photon with respect to a x-axis. In that case, the photon can either be in a semi state of where it's in a particular orientation in, that's inclined in a particular angle. In that case, it can be a zero or a one, and this makes quantum computing possible, and that's what defines a qubit. And the thing is, over here, because photons are in play and it's in the quantum realm, Schrodinger's equation and Schrodinger's cat scenario comes in play. Until you measure a value, it can be in a one or a zero. The moment you measure it, it loses its uh, energy. That is an energy dissipation as well, because you need to catch the photon at a particular angle. Like I said, if it's upward oriented and you're trying to get a signal of upward orientation, if you catch it at that moment, it's gonna give you that signal that you're looking for, but it is gonna stay like that moment it's stopping, and you cannot replicate that. It's gonna go out of orientation again, and this makes it very hard, and it goes also because it's in the quantum realm. It can be affected by other particles or other qubits, for example, inside the environment, and this is the main uh, features that define other topics that I'm going to talk about. That's part of quantum computing, and also sometimes can be a pro or a con when it comes to quantum computing. So just the overall takeaway from this slide is it's finicky, it's hard to keep it stable in a working condition, but it has a lot of pros as well, where it can be a superimposition of a lot of bits together. And the equation here is the wave function is either a 0 and 1 based on the angle, alpha and beta. And if when you measure it at a particular value, either the alpha or the beta would be 0. So the other value is measured properly. And yeah, uh, yeah, here qubit can be considered as an indecisive person, and this one, okay, uh, yeah, the qubit can be thought as an indecisive person. Again, going back to my example from the past slide, and this indecisive person can be a zero or a one at the same time, and that's the main thing that you need to take away from the differentiation between a qubit and a Shannon bit. And like I said, because it's in the quantum realm, there are other factors that come into play in a quantum computational environment, and a quantum computer that is computer science is obviously there. And then it's also governed by the principles of physics, because, like I said, it's in quantum mechanics that drive, and because wave functions are what defines the value of a qubit, math is there, and then inevitably electrical engineering there. So it's a much complex system. A quantum computing, for example, is a much complex system than a classical computer that we are used to, because The principles of math and physics are much quiet when it comes to a quantum functioning of a classical computer, but over here it's much dominant. Yeah. Okay, like I said, this is, for example, in this situation, I'm using the specific orientation of qubits, where the spin up is a 1 and the spin down is a 0. And these are called half spin particles, and these are basically created out of photons that are generated from high speed particles that are stuck upon, let's say, in a quantum computer, for example, back at Intel, the one that I have seen is something that is generated by high photons that are created by striking metals and laser beams on metals. And these particles are having certain orientations, and that's the example again I'm using here. And also, there are various ways of doing this. Like I said earlier, it can be polarized or based on the spin of the photon, or it also can be polarized by uh, the plane. And sometimes most of this polarization based on the plane is used for quantum communication, where it's a great tool. Quantum communication is great when it comes to quantum encryption and cryptography, because quantum signals in form of photons are much secure. Like I said in the earlier case, if you try to read that signal is destroyed. And when that signal is destroyed, obviously you cannot replicate it. So someone can always figure out that you're trying to tap into a secure line of communication. So that's another feature of quantum computing, and it's plus for communication as well. Okay, so like I said, quantum particles are in state where it either can be a 0 or a 1, and that measurement of that wave function is through the probability of how much it is of the particular orientation, whether it's as much of a 0 or 1. And that's based on this probabilistic amplitude. And the probabilistic amplitude defines whether it is a 0 and 1. And that's that's alpha I here in my example, and that I is the measurement that you get. And this like, let's say if you measure and you get a alpha I, then the square with a square of that with the sum of alpha j, which is the other orientation, is always a 1, because obviously probability it cannot be over 1. And yeah. uh, Okay. So when I am trying to talk about qubits of a particular qubit and measuring a qubit, they are usually done in something called an Hilbert space. And Hilbert spaces are what, uh, like I said, it's a vector form of a qubit, and each uh, zero and a one in that, which is our vector form, is called a ket. So it's the representation that's there for the 0 and the 1 state is called a 0 ket and a 1 ket. And okay, uh, so one of the first principles of quantum computing, like I said, is the ability to have multiple states within one qubit. So that is called superposition. And quantum superposition is one of the three basic principles of quantum computing. And like I said, the qubit is indecisive, and over here, the alpha 0 and alpha 1 are the probabilistic amplitude of it being a 0 or a 1. And like I said, the sum of the squares of both the amplitudes is always 1, because probability is always 1. So it's equally, it can be equal probable or it can be different, but it's basically based on the orientation at which this qubit is oriented towards. Uh, so, okay, and the next feature of a quantum computing environment is the ability to be in an entangled state. Over here, entangled states means, let's say there are two qubits. One is of a particular orientation and it's in a superposition state of its own, and it's next to another qubit in the same environment. If there are two qubits, because it's in a quantum environment, uh, properties of physics are going to obviously come in play. And this, let's say, one qubit that I represent here in one of my hands is going to have multiple, like, let's say, it'll have, obviously, it's a photon. So it'll have interactions with the other photon, which is the other qubit. And these make it entangled as well. So anything that happens to one on, let's say something happens to the one on the right side, it get affects the one on the left side as well. So if I'm trying to measure a qubit that's one in this picture which I'm showing you, and if I measure this as one, then two must be then two must be blue. Like if it like I said, it affects both, so you cannot have two of the same because, like I said, the spin is one. If the spin is up, the other one has to be down. Only thing is how much of it is up and down. And similarly, if it's the other one, the blue, then the second one should be red. That's how these two particles, because of this interaction, that's how they are affecting each other's composition and structure as well, which in turn gives us values of opposite. And quantum parallelism, uh, yeah, I didn't want to put any text in the slide because the best example is through looking at this picture. Because if you see over here in a normal computer, if there are, let's say it's looking, uh, okay, let's say someone's trying to figure out probable paths for all the all the drivers on the road in a city to get to the destination effectively. In a normal computer, it has to compute every other the driver's path independently and then get its value. Whereas in case of a quantum computer, it can bypass a lot of this uh, requirement of doing this linearly, and even sometimes it's much effective against parallel processing as well. And this it basically it gets you to the solution much faster than any other so, computational entity, because like I said, the earlier two possibilities where if one is affected by the other, let's say that again, just to make it small, let's say two people are trying to do something and one qubit represents and one user, the other one is the other user. If this person's path is affecting the other one, then you'll know which one to take and which one not to take much easier. So that's how a quantum computer is effective, and the feature of parallelism comes into play. So here, this is a Bloch sphere, and I'm just trying to depict this Bloch sphere here. And so the Bloch sphere is a 3D representation of a qubit, and like I said, the spins, let's say if it's up and down, that's on the z-axis, and this Bloch sphere, which is the yellow line, represents the wave function for that particular qubit, and it can be of any orientation based on its superposition. And let's say the wave function can also be represented with this equation over here, where theta is the angle between two axes, and the phi is the angle between the third axis to that plane. And let's say if I'm taking theta as a value between x and y axis, then phi is the value between the uh, xy plane and the z axis. And when you plug in those values there, you'll get the wave function for that particular uh, uh, qubit orientation based on its superposition. And yeah, just think about this being a small atom or a photon, and then its particular orientation is the wave function here. And so this is one example where I've taken up this this test that we can do. Let's say there are n number of bits in a classical system, and you're trying to figure out whether it's a zero or a one, and you have to go through two of n permutations, and one bit will be one of those two of n permutations. Whereas in a quantum system, it is of two of n possibilities of permutations, and it is not just one, but it is also everything of that. So, like I said, because you're trying to bring all the let's say there are two of n qubits, we're just trying to bring everything into a qubit, and it can be in a state of like alpha 0 plus beta 0, which is gonna give you the orientation of how the qubit is positioned. And this whole setup here of two to the power of n permutations is represented within this single qubit. That's the ability of a quantum computer, and that's where the speed, like the exponential speed, comes in play. And that's how, like, so the previous example on how a particular path is figured out and other stuff is figured out from the uh, parallelism possibilities as well. Okay, I'm just continuing the example, so explanation on Hilbert space. And like I said, Hilbert space is a vector space over complex numbers with inner product. And it is, these are some vector basics of vector inner product governing values. And Hilbert
Excuse me, sir.
space, yeah,
Hello.
yeah.
Can I ask question, sir?
Uh, yeah, I think we kept it for the last. Can
No,
we?
no. Without understanding that, we can't. I cannot
Oh,
proceed
okay,
further.
okay, sure.
That's why I'm asking.
Yeah, sure.
One question is, you said in one bit you can read or write many number of bits.
One
Whether it's
qubit.
it's one qubit. Because
Yes.
in one classical bit, either you can store one or zero. But you are
Yes.
telling you can, in one qubit you can store any values, 1 0 or
Uh,
one
uh,
one zero or like. My
yeah.
point is whether
So
it is a time dependent or it is anytime if you read you'll get zero.
no, 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 no. So the thing is, like I said, it's based on the orientation of how the photon is focused and the value you measure. But when you measure the value, it has to be of a particular wave function. And that wave function can be either a complete one or a complete zero, or it can be a superposition as well. Where I said that is where I said it is a mix of
Yeah,
a
yeah,
zero
I
and a zero.
understood that concept, sir. I understood that concept. My point is, if
Hmm.
I say stored 1 0 1 0 1 0, if I want
Hmm.
to read that value, when I can get 1 0 1 0, or sometimes I will get 0 0 0 also.
Ah, yes, yeah. So
So
that's
whatever I stored value, I need to get. So according to the qubit bit, that is spinning position only, we can get the value. So
yes.
how can I get the stored value get back? Whether I need to wait the spin to come to that position, or I can anytime I can read the values.
Okay. Okay, so let's say I take a qubit that's oriented to 0, and then I superimpose a qubit that's oriented to a 1. So it starts turning, obviously, because it's a 0 initially, and then it's a 1. So when it's a superimposition, it's neither a 0 or a 1, right? When I add the second one, when I or like I said, when I try and turn the orientation. So more and more you put, it changes in orientation and it becomes one particular wave function. And when you take that wave function and when you deduce that out, you'll understand how many of your values have come in. And yeah, actually, I'm gonna come on how it is done mathematically for the using tensor flow. I can talk more on that as I go down the slides.
Okay, sir.
Just I'm just giving you the physical. What I just mentioned earlier was the physics behind it, and how the orientation changes and how the superimposition happens. And to your question, I can say is, let's say there's a value of 0 of spin. When you change it slowly, it starts changing. It's not like in a normal Shannon bit where a 0, the moment you change it to 1, it becomes 1. But here it's superimposed. So the 0 and the 1 is there together in a qubit. When you do the add the second qubit, like the value of 1 into it. Yeah. So
No,
when you deduce it, it comes out based on, okay, let's say it was let's say it's a 0, and then the value of 1 is added. It becomes, it's neither up neither down. The probability is 50-50. The alpha and beta is zero point 0.5, zero point 0.5. So that means that there are two
no,
bits.
no, whether it is controllable, 0 or 1 by us.
Yeah, like I said, the orientation of the bit can be, a qubit can be changed based on a qubit is generated and then it's kept stable. I'm not getting into that whole explanation of the machines and system that's there, but it can be reoriented. Yes, if your question is, it can be reoriented on the physical side, which can be read out afterwards. But like I said, in
And
my example, yeah,
oh,
sorry,
one
you say
more
something.
question, sir. If I see the quantum computer, it's so big. It is not so small. But we are talking about
Yes.
quantum. It's very small. What is
Oh,
inside of that?
so when you, okay, let's say you've seen a quantum computer, it's like a huge tube and
Yeah,
there's
yeah.
something at
It's
the end, right? So,
hanging on the roof,
uh,
and then it's like there is a
okay,
huge things are there. And
uh,
when you talk about quantum, it's very small particle. Then I don't know what is this.
yes, yes. So let me just pull up a picture of a quantum computer in Satya Nadella's hand yesterday. Microsoft just showed a quantum computer yesterday, like the latest quantum chip. It's basically a normal chip.
One bit, one
It
qubit
can be in
computer.
one. Yes.
Yeah.
It can, you can just pull it out, and he was holding it in his hand. But the thing is, the whole mechanics that you see behind it is to keep it in a very stable state. Because these particles don't, like, obviously we know that nothing of that small magnitude exists in room temperature. So the big mechanism you see in a quantum computer's picture is from uh, from the cooling systems. Most of it is cooling control systems for the whole thing that runs, and the small chip is, I guess, it will be as big as one of these NVIDIA's what do you say, GPU accelerators. Yeah, in the link I pasted, it's from yesterday's news. You see, it's just the chip is actually something that can be held in someone's hand, but the problem here is it can't work in that state. It has to be in a very super cooled, controlled environment. And for example, uh, 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 okay, the last time I worked on a quantum computer with some code was for a grad school assignment, and I never, none of us. You can run a code on a quantum computer, but you can't see a quantum computer because they're all in labs. I can share the link to
Cloud.
one of, yeah, mostly they're cloud services, and these are shared because they're in labs, and these are all shared computational power so systems. You can't run you we can't at least uh, independent institutions, let's say, like Amrita, at the moment we can't have it until we have a lot of other mechanism that comes with it, and at the moment it's only just with big tech companies, and yeah, uh, that
One more question, sir. If I in the
yeah.
conventional method, if I have 4 bit 2 power 4, 16 values I
Mhm.
can store. What about in quantum? If I have 4 qubit,
so
how many values I can save?
so that depends on, again, I you can technically you can superimpose n number of values into a qubit. But the problem is
No,
there are some stability issues. For example, again, let me refer to something else. So recently, most of the qubits are still like 7 qubit. Most of the systems are still 7 qubit systems, and the stable ones. But there are some that I just don't know the max value. If you're asking me, I just don't remember
no,
on
sir.
top of
My
my head.
question is, if I have 4 bit in conventional, I can store 16 values 0002
Hmm.
11111. But if I have 4 qubit, how many values I can store? Whether I, because the
Ah,
combination is 000 and last one is 1111. In between values
yes.
only we can store. But qubit, how the qubit will help us to store more values? Still, I can't
Uh,
understand what it is behind this.
okay. Yeah, that's. Let me just. I think I need to show some. Yeah, when I go when I show that in a 2D
Because in
slide,
the
right?
previous slide you saw that some angle and for 2 power q power some more values are storing, but still I
Okay.
can't understand. If 4 bit means maximum 16 values we can store, but qubit, how the 4 qubits will store more values than 16?
Okay.
That is my question. Still I didn't get the answer for this. Anyway,
Yeah.
because
So,
this is a fundamental thing, I can't because I cannot come out from the conventional method to quantum method. That is a big drawback for me, I think.
okay.
Okay, sir. Please continue, sir. I will understand somehow.
Yeah. So I would like I understand the problem in visualization because we are used to something that's totally different from this. And trust me, like when I was trying to figure this out, when I started reading on this topic earlier, I've also had the same issue, and it's also got to do a lot with because, like I said, physics, math also comes into play here, and uh, yeah, so yeah, that's what it makes it a bit complicated, and yeah,
Because this is
like
the fundamental thing. Without understanding this, if they are talking
I
above all this, it is very difficult to understand, move further. That's why
yeah, so
I asked this.
uh, so the thing is, you need to visualize it as an atom rather than a signal. So when you start visualizing it as an atom in a 3D space, like I said, the Bloch sphere represents something in a 3D space. Then you can start looking at how a qubit works. If you I don't have it to ground. So if you look at something, let's say you have a ball in your hand and think that as a qubit, and the ball has a dot on one of the on it, and the dot, let's say you keep it on the top side, and that represents a particular orientation. And again, then the opposite of that, which is on the bottom, that represents the other orientation for, let's say, one and a zero here. And when you, again, these are subatomic particles, photons, there's energy in it. So when energy of two or different spins come together, it will obviously not be one of a particular orientation, right? Because energy it's stored in different forms, but it's
No,
never destroyed.
i-
So when
no,
what I'm trying to say is,
in such a case, sorry, sir, in such a
hmm,
case, can I read at a time three values 0, 1, or 0 or 1 like that? Or any
yeah, yeah, yeah,
quantum bit,
yeah.
any position, you said either 0 or 1. Sometimes
No,
0 or 1
what I
like that,
meant
you
is
said.
what I meant is 0 or 1 is defined as a particular spin. Like I said,
Correct. Correct.
if so, when you add much, again, I'm going to physics here. When you add energy again on top of something, it keeps changing, right? Let's say
That's correct. That's correct.
there is
Yeah.
some energy required to keep the bit in a particular orientation. Then you put more energy on it to change it in a different orientation. So obviously, all this energy together creates a wave function, and that wave function gives you a particular vector value. From that vector value, you can deduce the value of that super
No, 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 no.
and
My question, sir, if I store some value, I need to read that value. Whether I need to
yeah,
wait
yeah. So
until the
so
spin
you
has
have
to
to
come to the
deduce.
same position.
No, no, no. It will be spinning in that particular orientation, right? But you only know when you measure it. That's what I said. Schrodinger's principle also comes into play here. You won't know the value of that until you measure it. And when you measure it, you get the wave function value. And when you
Yeah.
get the wave functions value, is where you can deduce the other values based on the probabilistic amplitude. So it's a huge wave function. More and more qubits, more and more bits. Like again, let's say there is two to the power of n qubit system. Then the wave function will have that many values for you, and you have to deduce
Okay.
values out of that. Again, this is on the physics
So
side of it.
quantum physics is very important before go to the quantum
Yes,
computer. Right? So,
yes, yes.
okay,
Excuse
sir.
Yeah,
me.
Thank you, sir.
yeah.
Excuse me. I would like to, I think, I answer if the question of the Murli Bhaskar Venugopal, he was asking like how we can store multiple means 16 more than 16 values on 4 qubits.
Hmm.
I think
Yeah.
he's getting wrong in this way. According to my understanding, it is like that we can simultaneously store 16 values. Instead, in conventional computing system, we can store only one value on 4 bits
Yes.
among
Yes.
from 000 to 11,
Uh,
or we can store only one value. Instead, in quantum system, we can store multiple values by using a superposition. We can put the qubits into the superposition state using Hadamard gates, according to my understanding,
hmm.
and using that we can simultaneously process upon multiple states. I guess
Actually,
this.
okay, actually, I kept this for a few more slides later, but okay, let's talk about this right away because um, yeah, now that you've introduced the Adamat gate and stuff, just give me a second. I need to figure out which slide. Uh, okay, sorry. Yeah, so how Pooja mentioned, because Murli, over here, you need to understand that it's energy over here. In the classical system, it's either power is there for on, power is not there for off. But here, energy is there for off and on, but it's of different values. So for a zero, there's a particular energy. For one, there is a particular energy. So when you put these two energies together, then the total energy becomes different. And that is depicted by that wave function which I was talking to you. And when that energy is there, it won't be equal to the value of what the energy in zero is, or it won't be equal to the value of energy what is there in one. When you add more and more values of particular bits into it, it keeps changing. So that's how it's represented in a qubit. It's energy. So even in off state, there is energy, and that is why that's one of the reasons why a quantum computer or a quantum computer system uh, gates cannot be in a zero state because energy is the, let's say when you turn something off and make energy zero, energy is obviously going to be lost from the the controlled environment where this qubit is. And when energy is lost, it will affect the environment. If let's say a qubit is giving away energy, going to the classical system, let's say if the for qubit has energy, it is one. If it doesn't have energy, it's zero. In that case, when it becomes zero, it will give away energy. When it gives away energy, it will affect every other qubits and everything in that quantum chip, and the chip will become too hot. It can't and because quantum mechanics work better in a very subcooled temperature, this and loss of energy in the term of heat won't sustain. It will make this environment weak. It will break down. So that is why I said, even for zero there is a particular energy, for one there is a particular energy, and when you add more and more values to it, it lets you build on the total energy that's there in the system. And each energy, because it's in the photon, it has a wave function. And that wave function defines the, let's say, every other, obviously, it's in a wave, right? The amplitudes are going to be again different for every time an energy is added, the wave pattern changes. And each pattern represents the qubit total number of bits that are stored in it. I hope it's better now.
Yes, sir. There is.
Actually, madam said in 4-bit we can store more than 16. What do you mean by that, ma'am? 000 111 is the last number. What is the more than 16 values?
No.
No, sir, it's
What?
not more than 16 values. It's like simultaneously we can store more than one value. In conventional
Yes.
system, we can store only one value at a time. And in
Okay.
quantum system, we can simultaneously store more than one values among those 16 values due to
Okay.
superposition.
Yes, ma'am. Good. Now, the spin position will know that whether it is a 0 or 1. So spin is always spinning. In that case, I need to wait whether the spin to come to the position to read the value, or I can anytime I can get the value. This is my question.
This the spin is always happening. The orientation of the spin is what defines the value. Like I said in this,
Yeah. So I need to wait
so
to get my
orientation is
decision
what
value.
changes. Murli, let's
Orientation
look
will
at
not
this.
change.
No, if you look at this picture, see, one is up, zero is down. When you obviously
Correct.
there's energy in two of these photons, right? When you bring it together, obviously it can't be up and down, right? It will be something else. Is that correct? By normal physics, when two
Yes,
particles
sir.
of energy come together of different values, let's say one is pulling that side, the other one is pulling this side, and when they come together, it can't be like this. It has to be something else. That's agreeable.
Yes, sir.
Yeah, so that is what Pooja mentioned earlier. When you add two energies together, it will change orientation. This let's say one is up, one is down. It might be like this, it might be like this, but for sure it's not up or down, right? When it becomes a single one. So that is
What
what
is
is
the material
superposition.
they are using for quantum computing,
Uh,
sir? Because we know that conventional computer
photons.
silicon is no.
Yes,
Photon is there for all material. Is there any
yes.
specific material to quantum?
There's no specific like again there are for example Intel is latest Intel quantum is based on electrons, and it's on a semiconductor, and some of the
No,
quantum
I'm
computers
talking about material, sir. Material. Whether it is
that
extracted from silicon or German or
no
some other
no
material there.
like that. Yeah, that's what I'm trying to say. There are silicon based quantum computers. Then
Quantum.
there are non-silicon based quantum computers as well. And these are, just because I said silicon, don't get misguided on the fact that it is just like a conventional system. Silicon over here gives the electrons that are needed for that. If
That
you
that
Google, I
I
think
agree.
it's
That I agree. Yeah, in the very
yeah.
first slide you said that when you want to make it a small size, the conventional computer is not working. But if you can take as energy as a photon, then that will be working perfectly. That's what you said in the first slide. I agree.
Yes.
Um,
So
yeah,
so it is like, let's say, Uh, for example, I guess if you can Google it's called tunnel faults. That's the name of Intel's quantum computing chip. That's totally based on semiconductor technology, and it's on silicon. And this, if I believe the link which I shared for Microsoft's quantum computer is based on photons, and it's some of these photons are created by high intensity light hitting through metal. The double slit test, these photons are made from those. Like uh, when light is passed through a barrier with a small slit, it creates
Yes. Yeah.
these photons. Yeah. So these some of these are made from some of the qubits are made from those. So these depend upon it's like proprietary software. So we don't know much about it. We only know the physics and the principles behind it. If you're asking question like what it is made of, we can say it's photon electrons, but other than that, I can't say what it is made from until I like you are the hands-on person working on that technology for that that lab.
One
So
one more question, sir. The qubit
yeah,
is used to store the data, and what is the CPU they are manufacturing, sir, in quantum computing? Central processing unit
the
using qubit.
so
Using qubit
the
or
quantum chip, just like
Sorry to
no.
interrupt you. Sorry to interrupt you, Murli Bhaskaran sir. Shall we have a question answering system at the end?
Madam, sorry, ma'am, because this is a very basic things. Because quantum computing is a emerging technology, and without understanding the fundamentals, if you learn anything, that we
No,
cannot go
That
further.
I can
That is
understand,
why I'm.
sir. Your questions are valuable question, but the thing is, let the speaker complete a presentation.
yeah,
Then we can have a question answering system, sir.
Okay, madam. Thank you, madam. Thank you.
Okay, sir.
Thank you,
Thank you,
sir.
sir.
Very nice interaction.
yeah, yeah. Give me like 50 more minutes. I think I should be done by then, and we can talk after that. Uh, okay. So yeah, I know it's a lot of physics here, and it's a bit hard to digest when we are not conventionally used to this conversation. And yeah, but continuing, I think I finished this, right? Uh, yeah, okay. So over here, to give more sense to what I was trying to say, the wave function can be also depicted as a of 0 plus b of 0. Let's say the a and b are again the probabilistic amplitude, but uh, these are all matrices. Let's say 1 of 0 is for this particular 0 orientation, and the other one is 0 of 1 matrix, which is 2 cross 1 matrix. And if these depict each other, the sum of these two, I guess this might help you understand more about what I was trying to say. These two will become the new value. So let's say 0 is a 2 cross 1 matrix of 1 0, and the other one is 0 1, the values. And then you get a new one that is AB. That's what kind of superposition talks about. And yeah, so uh, like I said, the wave function is the sum of all the energy that's put into it. For example, let's say, like I said earlier, if the orientation of the qubit is initially 0, then more energy is put into it. Let's say if again a 1 or something, then it changes. And every time an energy is put in, it changes. And this is the final value. For example, in this case is AB, where it's just two qubits that are put together into superposition. Superposition here is again, to bring clarity to what I was saying, it's like putting multiple energy impulses into a single atom sorry, not atom, photon or an electron. It's like trying to put everything into one single physical particle that's there in the processor. And as Pooja earlier mentioned, the Hamad gates are what uh, helps in getting a particular value into superposition state. And let's say there is a zero value, and when it goes through an AMAR gate, it gets into a superposition value. And again, uh, just to make uh, things simple, uh, again, let's say your AMAR gate is every time it it's that gate that lets you does superposition to a particular qubit. It's like someone is trying to tilt the orientation to according to the latest value. That's what, to put it in simple layman terms, that could be what AMAR gate is to you. And when you do this twice, you get back to the opposite of what it is. So uh, when you Ahmad gate, like I said, you put energy every time for superposition. Once for first time when you put energy through an Ahmad gate, it changes into a non-zero. A zero will become a non-zero, and then again the Ahmad gate will do something else to bring it back to the other side. It's basically most of the quantum gates tilt the orientation of the qubit uh, based on what the gate is. For example, Pauli's gate does it by pi radians, each and every Pauli's gate on the axis. Like Pauli's x, there's something called Pauli's x-axis gate, which will turn the qubit on the x-axis by pi, the value of pi radians, not and degrees. I mean radians. And same thing for Pauli's y, Pauli's z. So these are gates that turn the orientation of the qubit. So, as I was trying to explain to Murli earlier, the orientation is what defines the value that is within the qubit. And these gates don't change the energy, but it changes the orientation. When energy is given, it the gate changes the orientation according to the present new value of that qubit that's stored there. That's the energy. So, like I said, a zero going through two Hamad gates will become a one. It's like a NOT gate that we are used to. But again, it's not that simple because here it's the photon at that level, photon, or again, it can also be an electron. So it's that level where it is reoriented, changed, and refocused. Um, so the CN gate is another. Again, I'm not going through every gate that's there in quantum computing environment. I'm just giving some highlights, and the reason why it is. I'll just come down to like the gate that over here. C naught gate is with one control value and the target value, and it's in this truth table, you can see that when the value of the B, sorry, yeah, uh, it just inverts the value of the bit over here, and it's very similar to the XOR gate here. And the again, this is orientation that's eventually changed at subatomic physical level here, not the not like the switches that you're used to. And the other okay, now this is an example of a quantum circuit with certain gates to do multiplication by two. And yeah, so if you see the zero value, when it's the input is zero and it's zero. But when I multiply these two, it gets to two over here. And that's I'm just giving an example. I guess yeah, we are running short of time as well. So yeah, 1 minute. Yeah, yeah. So like I said, this is an example of multiplication by two, and this over here is actually just two cross switched C naught gates, where it just changes based on the control value over here. And I'm just skipping through this to make time. And so this is another CC not. It's a control not gate over here, and this is equivalent to a NAND gate. sorry, NAND gate here because coming to what I was trying to say. So NAND gates and NOT gates are basic fundamentals of what is there within a processor. And the best way to go back is trying to figure out the fundamental gates that we are very similar to, so that we can at least make processors that are fundamentally similar in functioning. And and the thing is, one thing over here, most of the gates are having control gates, not they call control gates and target gates because energy is not lost here. So you can't say that okay, this the switch is turned zero and it's gone to a different value. Basically, like I said earlier, energy has to go somewhere, and only it just jumps from one place to the other. Like if let's say two control gates are there, it will just affect the third one, and because obviously all these are in the same environment as well. Uh, yeah. Uh, just taking a segue to something else here. I uh, I just wanted to talk about quantum cryptography, and quantum cryptography uses same principles of quantum computing in the physical layer where it's still a photon. And an example over here, which I'm showing you, is how let's say there's a there's someone trying to send from this light source on the left side, and someone's trying to catch it on the right side. And the thing is, it let's say you just like a private key and a public key, you just tell them which set they should use on the other side, and they keep that film filter there, and they send the signal here, and you can cross check over here, and yeah. So what happens here is when you're sending once, they have a again the orientation here in this picture. I tried getting something similar to what we were used to in the other slides, but I couldn't get one. So over here, the orientation for ones and zeros are a bit different, but what they're trying to do is they're sending ones and caught in a filter accordingly that works for that particular orientation of zeros and ones. And when the user gets it, it's fine. If someone, let's say, like I said, I mentioned earlier, if someone tries to measure a value of a qubit, this photon which is passed, these are mostly passed through, let's say, optical fiber cables. When you send a photon through the optical fiber cable and someone taps in, this signal is lost, and then the person who's receiving it can understand that someone's trying to interfere in it, and someone's tapping in on this communication. So that's the other uh, benefit of quantum computing and quantum cryptography is this is how it's encrypting by itself. You don't you don't need a particular this is you don't need any other encryption because already the particular orientation, the energy orientation of that qubit itself is known only to the sender and the receiver. And if someone's trying to meddle with it, it's lost, or it's the orientation is changed, or it can't be received properly because obviously the receiver is hitting with the particular set of filter that reads the signals. And yeah, so uh, yeah, this is one picture I got for the quantum computer. And if you see, this is a huge apparatus, like just like how Murli asked earlier, this is a huge thing. So actually, if you see, the chip is at the leg, the end of the bottom part of the whole apparatus, and everything else is like a control system, a cooling system, and these are all again in a very subcooled lab environment. And the chip is, if you look at a quantum chip, it just looks like a huge graphic accelerator chip. It's not as small as what you see in a personal computer, but it is quite big. And yeah, the whole other system that you see on top of this chip, which is like a cone, is just a cooling system, the control system, and everything else that comes along with it, because this is where the measurements happen. So the measuring apparatus, everything is the use thing. The chip is just the functioning environment on which the qubits are kept on. And yeah, so like this is an example of an Intel quantum hardware where we have a quantum. Like I said earlier, these machines are in lab setups, and we only get a simulator. Like when you plug in to the cloud system that all these companies have, is you get into the basic simulator level setup where each and every time when you do something on your machine, it simulates it in the quantum computer and comes back with the results. So that's how it's working at the moment, and there's a lot of room to go. And even when companies are saying that we achieved this like say petaflops of computational power, it's it's on this computer where they had their whole thing for themselves, and they were running it on their controlled environment. And yeah, that's again, uh, yeah, you don't know much about these experiments that they say, other than that they achieved the goal of so many petaflops of computational runs and so that, because everyone's in a development stage, and I guess no one wants to give away much of information on what is this, how are these things done. We just know that the chip is the small thing at the bottom, then the whole setup is the apparatus that runs the whole computer. And it can be something similar to the old mainframes computers back in the 60s, where it is huge. Now the classical computers become very small. It's like even the phone on our hand is a classical computer, right? So hopefully it will become smaller and smaller and more stable in a room temperature. There are like for mention, there are quantum computers based on diamond dice. Last I checked, where it's on room temperature, but the biggest con in that is it is very easily affected by other environmental constraints within it. So like anything else, let's say you're having a radio running on the side, that radio signal will affect the quantum computer. And let's say you have a light beam, that will affect it. So these because these are all energy dissipated in different form, these are all a factor that affects the quantum chip. That's why the chip is within a very controlled environment under a particular temperature. Yeah, yeah, I guess so we can have some Q&A. Sorry.
Yes, the participants, now you can ask questions.
Yeah, again, rider is, it's a bit overwhelming if you're new to it, and also visualization is a big requirement here, because we just don't see when we do like let's say you're doing a lab experiment for a small adder based on switches. It's very easy to do it and see in front of you, but over here it's a bit complex. And trust me, I just skipped through the main highlight topics. I didn't even get into a lot of the math or uh, yeah, but yeah, this is just the overview of basics.
Very interesting, sir. Thank you very much. And when we'll expect the quantum laptop?
No idea. I can't even like working for a computer that a company that makes chips for the classical computers. I can't even say whether when we can expect a 14 Armstrong chip or a 18 Armstrong chip, because we are trying our best, but it's not happening. So this is like, I don't know. It's at least a few. I'll say a
The
decade or
Intel
more, right?
quantum computing is in USA, sir. Which place in quantum computing is there? Intel. This
Uh,
device.
uh, it's just not just one, right? So Intel, it's based on Intel's. So there is a sub company within Intel called Intel Labs, and Intel Labs are the ones who run these projects. These are all in uh, like experimental test phases, not even for commercial use. It's just that companies are doing all this for just to be ahead on the race when some breakthrough happens. Sorry, Pooja, you were asking something.
Okay.
Yes, sir. The information you provided was really good and quite informative it was. So I was asking that currently I am working on quantum optimization. I'm
Okay.
doing research on that. So are there some opportunities that I can get to collab with in this field?
Okay. So one thing is, at least when it comes to job prospects or research prospects, there's a lot of how would I say this? There's a lot of educational and laboratorial experience required. So I can't say much about it until yeah, until I know more about what you're trying to achieve.
I want
Like,
to collab in research basically. I want to pursue teaching career. So during the
okay.
career, I want to continue my research as well. So
So
that I want to pursue in collaboration.
So, for example, even I don't know much about the curriculum back in India now, but when I went to grad school here in University of Maryland, there was just one professor who was taking this course. So, and it's always that professor. And this course is less taken, and especially because it's quite heavy on math. And the research, if you're asking me, there's not much research until you're in a top Ivy League or a top university in the US, because most of them don't even have the computers. They always have tie-ups with any other company because these are few $1 million for all these computers. So to start with, the best option is to collab with others who are at least researching and academics and who are on this field. Uh, yeah, and yeah, I'm a person with computer science background, and most of the people who work in my company I was just doing my own analysis to figure out who are these guys who are working on it. They're all people who are theoretical physicists, and they are chemists, like they are PhD holders in physics, chemistry, and math, and less on computer science because it's still in the realm of development, and yeah, I would say that.
Mhm. Okay, okay. Thank you so much, sir.
Yeah.
Any other participants can raise their hands or can put their questions in chat. Thank you, Mr. Pranav Menon, for an illuminating session on the mechanics of quantum computing. Your insights into quantum superiority have surely expanded our understanding this fascinating domain. It was a wonderful session, sir. Thank you
Siddharth,
again.
Yeah.
Yes,
Siddharth,
ma'am.
Thank you.
Yes, ma'am.
Siddharth,
Yes, ma'am.
there's a
Yes, ma'am.
question in the chat. There's a question
Oh,
in
Oh,
the chat.
sorry, that was a question.
okay. Sir, before you leave, could you
How
please mind
does
answer this
qubits
question? Okay, sir, I'll just
how
read it, sir.
does qubits play a role in
And
cybersecurity based quantum security application? Yeah. So Anand, like I said, qubits. The biggest thing is it's used for communication where uh, when a qubit, like I said, when a qubit is measured, you need to capture the value, right? And then that is altered. Whatever external for like the measuring process is itself an external. Uh, just sorry, just Uh, the measuring process itself an external interference, and when this interference is happening, tampering is figured out. So that is one of I think over here some projects are. I'm just not able to recollect the names over the top of my head, but the competition is big between China and US over here. And this is quantum cryptography and quantum communication. The leaders over here is actually the government organizations and institutions related to that, while in quantum computer development is between big tech companies. Over here, it's the governments, like the Chinese government. I think they have a quantum uh, system-based satellite as well, if I'm right. I also uh, they have laid communication like lines between cities on fiber optics where quantum signals are sent, and yeah, so some explanation, like some elaboration on these possibilities are all those, and I guess it's much the like in the quantum world there are like two different things. One is the computers, and then the realm of cyber and quantum security, and these are uh, two different paths that you can go down when you're trying to learn on them. And yeah, sorry, that's the next question. What's the difference between qubit and quantum dots automata implementation? Uh, I don't understand what is quantum dot automata implementation. Sorry, I'm not able to understand that question. Thanks, ma'am. Yeah, quantum key distribution. Yes, yeah, that's one of the basic uh, implementation of quantum uh, computing and security. Yep. Yeah, I think that's again. Let me just find the company name. Uh, if you guys want to try some programming, let me share this particular link. It's IBM Quantum Computer. So IBM has have their own quantum computing platform. I'm sharing that link. You can try a few basic quantum yeah, but do note that it's timed. You only get a particular number of hours, like not even hours, few minutes per day. It's free, but yeah, you can play around in that. This is one good. Again, it's a cloud service. You're not seeing a machine or anything. You don't even see what's happening in the machine. You can just run some code and it comes back to you. Like for example, in my grad school, I think it was implementation of Shor's algorithm as a as a question for the finals exam. So we had to implement it in this machine, and we had to give the solution that comes out of it. And I, yeah, there's some requirements on. Yeah, that's one example of how it's. I have used this in past.